The goal was to have array time performance but to be space efficient. Right? So arrays give us order one operations, lookup, insert, delete. But we have to allocate a space which is equal to the size of the key universe, and that's often too expensive. So we've thought about ways to reduce that space. We have the idea of a hash function, H, which maps the key space of values in the range 1 through m into some smaller space ranging from 1 to s, where s is much smaller than the key space. Hopefully, right, in an ideal world, s is going to be roughly equal to the number of items that I want to store, which I'll denote by n. The idea being that obviously it's going to take me at least n space to store the items. So that's a lower bound, and the question is whether I can achieve that as an upper bound as well. Okay. And we observed last time that there is no one good hash function for all sets of keys, because for any hash function, there's a large set of keys that will all map to the same bucket, right? We'll call these buckets. And we can store all those keys in the bucket by just throwing in a linked list, which is only going to cost us an additional n space. However, the lookup time is now going, or insert time or whatever, is now going to be proportional to the size of the bucket. And we're going to lose the order 1 performance that we want. Okay. But we also argued that a random hash function is good in expectation. Okay. We proved that the expected number of collisions with a particular item I was at most 1, just counting itself. Sorry, that's not needed in the definition of collisions, is just the total number of items divided by the space that we're mapping into. And so that means that the operation times their expectation is at most 1 plus n over s. Okay. Now, it's important to remember that this is an expectation, right? Using randomization does not suddenly mean that there's a good hash function. It means that the average cost, the average collisions in the hash function are small, but that you can still be unlucky and end up choosing a random hash function that maps everything to the same bucket and ending up with slow operations. Okay. However, this is something that you can argue formally. Right. So when people are introduced to hashing in undergraduate algorithms classes, often the teachers just tell them, let's assume the keys are random, right? Or what's called the uniform hashing assumption, right? And if you just assume the keys are random, you can say, yes, on average, the lookups will be fast, but that's a pretty gigantic assumption. Here, we're not making any assumptions at all, right? The randomness is chosen as part of the algorithm. And that means that we can formally prove that the expectation has this small value. Well, we did that last time, that we observed that a random hash function is pretty good. Sorry, hang on a sec. That's so strange. sorry, give me just a minute. There we go. The problem with the random hash function is that a random h can't be stored efficiently. You need to remember your random hash function in order to be able to look things up after you've used it to store things. And so using a random one won't work, a purely random one. So our goal was to find a small hash function. And while we're at it, let's also ask that it be easy to evaluate. Or sorry, let's not use easy, but fast to evaluate. That acts random, right? It won't be truly random, but it will be random enough for the purposes of hashing. And for that purpose, last time I argued that our analysis required only pairwise independence. Which is to say that the probability that some first key maps to X conditioned on some other key mapping to Y should be equal 1 over S, right? That was the crux of our expectation analysis, right? We introduced indicator variables and we argued that the expected value of one of these indicator variables for a collision of a pair of items was 1 over S. So if we can, but that only is about the two items I and J. So if we can just make sure that the two items I and J act independently of one another, we can make the same analysis and we can conclude the same expected bound on the expected number of collisions and therefore on the runtime of the hash function operations. I showed you 3 coins last time, right? Where any two are pairwise independent, but they are not mutually independent. Right? So we are now going to generalize this. And to do this, we are going to use a tiny bit of algebra, the advanced kind, not the high school kind. Let's suppose for a moment that S is a prime number P. Okay. What I'm going to show you is the Carter-Wegman trick for hashing, which is to map a particular value X into the value AX plus B mod P. Okay. And what I'm going to do is I'm going to define my function H sub AB where I choose a random A and B. Okay. And my claim is that if I choose a random H sub AB hash function by choosing A and B at random, the result is that the positions, the buckets for any two keys are pairwise independent. In particular, if A and B are chosen uniformly at random from the range 0 to p minus 1, then, and sorry, this is denoted by UAR, then HAB of X and HAB of Y are uniform over the range of values 0 to p minus 1, and also pairwise independent. Okay. So if this is true, then HAB is the kind of hash function we want, in that the expected number of collisions will be small for any item. Any questions about why this is what we want to prove, why this would be sufficient to give us a good hash function?
Just a quick question. P is fixed, right?
Correct. P is fixed. P is not random. P is just the size of my hash table.
Okay.
Okay.
How big do we choose P?
Well, as I said, for the moment, just take P to be the size of my hash table. I'm just going to assume that my hash table has prime size. We're going to have to fix that assumption later, but I'm going to get there one step at a time. All right, so how do we prove this? Well, what we're interested in is the probability that H sub AB of X is equal to some S, and H sub AB of T, of Y is equal to some T, where X is not equal to Y. Okay, now what is that probability if we had a truly random function that mapped X and S both, X and Y both to the range from 0 to P minus 1?
Just 1 over P.
It's just 1 over P, right? P possible values. And I mean, you do need to look at this, but you can prove that HAB of X is uniform, right? Sorry, if you have a random function, then certainly it's clear that all of the positions for S, for all the values of S are equally likely, all the values of Y are equally likely, so the probability that they're equal is 1 over P. But now we're not working with an what was that?
So I have a quick question. Are S and T the same, or are they different values?
It doesn't matter.
Okay.
They are any two values.
Right.
So so what we've just said is that the probability of any particular, sorry, we should be more particular. If these are truly random, right, the probability that H of X is S and that H of Y is T, well, on a random function, they're fully independent, right? So this probability should be equal to 1 over P squared if these things are independent, right? Because every value is equally likely. But let's look at the pairwise independent case. We can rewrite this as the probability that AX plus B is equal to S and AY plus B is equal to T. So I can write that out in a slightly different matrix form. If I say AX plus B times 1 equals S, and AY plus B times 1 equals T, right? In matrix notation, this is just saying that the matrix that looks like this times the AB vector is equal to the ST vector, right? Now, when you have a matrix equation like this, how do you solve it? Or how do you know if it is solvable?
You take the
Look at the-
determinant.
Right. You take the determinant, right? I mean, the solution is that AB is equal to the inverse of this matrix times ST if the determinant is non-zero. Right? If the determinant is zero, you don't have a solution, or you can have a multiplicity of solutions. But if the determinant is not equal to zero, well, what does that mean? The determinant is not equal to zero. What's the determinant here?
X minus Y.
Right. So as long as X is not equal to Y, there is a unique solution. In other words, a unique pair of values, A and B, right? Now, this is where we are using a little bit of abstract algebra, right? So we're used to this kind of argument when our matrices are real numbers. Now we're actually operating mod p over the integers mod p. And so it's important to remember that mod p is a field. And so basically algebra works. All the things that we're used to doing, subtracting, dividing, so on and so forth, can be defined mod p. And so this matrix algebra also works mod p, and this argument that there is a unique solution also works when we're thinking about algebra mod p.
I think AB should be x1, x1, y1 inverse.
AB should be, oh, sorry. Yeah, that's right. I need a -1 here. Yes? And that's the point. We can only do that inversion if the determinant is not zero. Okay, so again, modulo this aspect of modulo, we have a unique solution. So if the solution is unique, what does that tell us about the probability that HAB of X is equal to S and HAB of Y is equal to T? Well, the probability that the event that happens is the event that we pick this just this unique A and B, right? In order to get this outcome, we have to pick this the appropriate unique A and B that solves this equation. What's the probability that we do that?
1 over p squared.
It's 1 over p squared, right? Because each of A and B is being chosen from 0 through p minus 1. And so we have exactly what we want, right? The probability that any outcome for this pair of items is the same as its probability under a random function. So from the perspective of any pair of items, this function looks random. And that's saying that these two items' positions in the buckets are pairwise independent. Any questions about that? It also, along the way, tells us that the position of the items is uniformly distributed, right? Because they look just like random items. So every bucket is equally likely to get each item. So that's great. That tells us that if we're willing to have a prime size hash table, we can get expected order 1 lookups, right? In a prime size table. But what if the size S of our table is not prime?
Move the board down a little bit. I can't see it.
Sorry, thank you. What if S is not prime? What do we do? Well, we actually already did all the hard work. What I'll do is I'm going to choose an S which is much, much bigger than P. Sorry, I'm going to choose a P which is much, much bigger than S. We'll come back to how big it should be in a minute. And now I'm going to slightly modify my definition to hash key X. I'm going to compute AX plus B mod P, just as I did before. But now I'm going to take that whole thing and compute it mod S. Okay. And I claim that that's going to be just fine. We're still going to have uniformly distributed, or a basically uniformly distributed hash table, and we're still going to have order 1 lookups. Okay. Why is that? Well, the point is that we know that our HAB function spread things out uniformly and pairwise independently. And as a result, right, when we collapse that to a table of size S, they're going to be they're going to be close to uniform. And I'll show you that in a picture in just a sec. And still pairwise independent. And the way to see that pictorially is that I can take my table of size S and think of it as a ring. And now my table of size P can just be thought of as wrapping around and around this ring. Okay. And so any item that gets computed mod P then gets projected down to the corresponding bucket in the table of size S. Okay. So from this picture, we can see that every bucket has about the same probability of getting an item, right? Because we know that the items are uniformly placed on the spiral. And so if they're uniformly placed on the spiral, then every bucket has about the same number of origins on the spiral, right? Now, every bucket will not have exactly the same number of spiral positions. How come? I claim there's going to have to be a slight imbalance.
Because P is prime.
Exactly. P is prime, right? If P were divisible by S, then we would get the same number of spiral positions for every point, for every bucket. But that's not the case because P is prime. But we're only off by 1, right? So each bucket has the same number of spiral elements, plus or minus 1, right? And so that means that the probabilities for the different buckets only differ by something like plus or minus S over P, right?
I have a quick question.
Yes.
Are we assuming that P is much larger, like is larger than the largest possible value of X?
Very good point. Let's just hold that for 1 sec while I finish this argument. I did want to get to it, but yes. Okay. So there's a difference of probabilities by only S over P. So if, for example, we set P equal to N times S, right? Then the bucket probabilities differ by only 1 over N, and you can go back and show in the analysis that this only changes our expected collisions by order 1. Okay. So coming back to what was just asked, it is crucial that in addition to being significantly larger than S, we also need P to be bigger than the maximum key size. Right? Why is that?
Well, if X minus Y is divisible by P, then
Exactly. If we have two keys that differ by P, then they will always map to the same location, and our argument for pairwise independence breaks down, right? And this comes right back to the analysis we did of pairwise independence, right? I was doing everything mod P, and so implicitly I was assuming that X and Y were mod P. So there is no difference between two numbers if they differ by exactly P, if you're considering them mod P. Okay, so yes, P has to be bigger than the key size and also wants to be bigger than, N. But remember, P is just an integer. It's not a data structure. So it can be really big. Again, P can be 2 to the 64 and we're fine. Now, 2 to the 64 is not a prime, but it's a prime power. And so a lot of things still work with prime powers also. All right, so any questions about that? We have now sort of completed this analysis, right? We've shown that by choosing a random a random hash function from this so-called 2 universal family, where we just specify A and B and do a simple linear computation to find the bucket, that gives us pairwise independence in the position of items. And that means that we have an expected load of 1 or of a constant. And so we have constant time lookup, insert, and delete. As long as our table size is larger than N.
Excuse me,
Yes,
could you go to the previous board?
could I what?
Could you bring just the previous board?
Yeah,
Can't we put 1 over P for the error probability?
yes. I think that's correct. But again, the point is that we have lots of wiggle room. We can make P really, really big, right? Because S is going to be some, S is going to be some number like, the size of our data structure, right? So it's going to be in the thousands or the millions or the billions. Whereas P just needs to be an integer that fits in our computer. So it can be 2 to the 64 or even larger. So there's really no problem with that slight round off.
And one other thing, I think the assumption of pairwise independence becomes again approximately true.
Does it become? So it might, but again, by only this negligible amount.
Correct.
Okay.
Thanks.
I think you actually may still have pairwise independence, but it doesn't matter. So I don't want to stop to figure it out on the fly. If you want me to check, I can email me and I can verify it out later.
Okay, thanks.
Sure. Okay. So all we need to do now is store 2 integers. A and B, and we have order 1 operations. In expectation. So expectation is nice in general, right? Over a large number of operations, you expect things to regress to the mean. And so, you know, your average cost will almost certainly converge to the expected cost. But it is interesting to ask about the maximum load. Like how many items can end up in the same bucket with some probability. And it turns out that you can prove that the maximum load is order of square root of n with probability 1 minus 1 over n. So it is, if you use this pairwise independent hash function, it is very unlikely that you will have more than square root of n items in a single bucket. Okay. More generally, right, because this is only an expectation, we do know that, you know, it's quite likely that some items will have a larger load. But fortunately, they're sort of random items, and they are unlikely to be searched for often. And so the fact that some of your operations are a little bit slow doesn't affect the overall expected runtime. Sort of interesting little side note for the more theoretically inclined among you. Some theoreticians have proven that there do in fact exist pairwise independent hash families where this root n max load is very likely. So having a load of square root of n almost always happens, but because it's only involving root n of the items, it doesn't disrupt the average, and you still get an average lookup cost of order 1. Okay. So we're now done with getting a data structure that is good in expectation. Any questions about it?
Excuse me, can you please compare this with the, so in the previous section, we got that with S buckets, we get expectation collision of
S over n. Yes. Oh, thank you very much. So I kind of jumped the gun and assumed things. So we actually showed an operation cost of 1 plus or of an expected cost of 1 plus S over n, right? Or sorry, n over S, where S is our space and n is the number of items. Shoot, sorry, all my pens are dying. N items into S space. Yes? So in particular, if we set S equal to n, this becomes order 1. Right? So in linear space, we can store items with expected order 1 operation cost. Obviously, if the space is much less than n, we can't do that, but we don't need more than n. Okay?
But I mean, sorry, I'm a bit confused. Why is in the upper bound we don't have any S?
Which upper bound?
I guess I didn't understand the argument, the square root of n.
Oh, so that's if you map from n items into n items. Okay? Sorry, so that's what I meant about jumping the gun. So what we've proven is an S over n is an n over S bound. And so that means that we can set S equal n. And this analysis here of the sort of worst case performance is an analysis that applies when S is set to n. It generalizes to other values of S, but n is what we want in general, so that's what it focuses on. Okay. So any other, thank you, those were informative questions. Does anybody else have questions? So I've got one that the theoreticians asked. Can we guarantee order 1 lookups? Right. Which goes right against what I was saying before about how, well, if you pick a random hash function, there's a good chance that in expectation it's good, but there's always a problem, right? So how can I get around that? Well, I'm going to assume that I'm given my keys in advance. Okay. So it's true that for a random hash function, there's always a bad set of keys. But I'm now going to ask, that may be true, but if I know what the keys are, I won't use that hash function. Can I find a hash function that is always good? Or sorry, can I always find a good hash function if I'm allowed to look at the keys while I'm hunting for the hash function? And let's be really ambitious. Let's try to arrange for no collisions at all. And this would be what is called a perfect hash function. Now, obviously, if we want a perfect hash function, the space is going to have to be larger than the number of keys, right? But nothing that we've done yet lets us get a perfect hash function for any space at all. So let me creep up on this notion of a guarantee. Let's talk about the chance of no collisions. If we use a random hash function. So I'm going to creep up on this in a standard way. Why don't I ask about the expected total number of collisions? Can anybody who remembers last lecture give me a formula for this expectation in terms of the indicator variables that we worked with last time?
Just a double sum
Exactly.
of the
A
probability
double sum of what?
of the probability of I equals J times the indicator.
Exactly. So I defined last time these indicator variables Cij for where the ith item collides with the jth item, right? And if I just count up the number of collisions, well, that is the number of collisions. But this, of course, is equal to the sum of the expectation of theCijs, right? And I should be clear here that now we're doing a double sum, right? When last time we counted collisions with I, and so we only summed over J. Now I'm counting the total number of collisions, and so I'm looking at the sum over pairs I and J. Okay. So what's the value of this expectation? Well, that's a collision probability. And what is that probability if I'm using a random function?
Doesn't it double count?
Yeah, sure. Let's just do a summation over I less than J to avoid double counting. Thank you. So what's the probability that I and J collide?
1 over S.
1 over S. And how many things are there in my summation? How many terms? Well, I'm looking at every pair of items, right? So how many pairs of items are there? It's n choose 2, right? How many ways can I choose a pair of items? And this is roughly n squared over 2. Oops. Times s, right?
Wait, shouldn't the s be in the denominator?
Yes, thank you. Yes? So in particular, if s is at least n, then this quantity is less than or equal to a half. Sorry, n squared. So if I use quadratic space, there's a 50-50 chance that I will have, the expected number of collisions will be 1/2, right? Now that's pretty nice, but a half is not 0, right? On the other hand, we can't really have half a collision, right? So we can use a well-known method to get from half a collision to 0 collisions, right? So we now know, and this is, I think I showed you 4 things you needed last time from probability. We needed indicator variables. We needed linearity of expectation. We needed independence. And I introduced you to pairwise independence. And now we're going to use what's called Markov's inequality. Which I think is the last thing you need to know. Markov's inequality says that if x is a non-negative random variable and its expectation is less than t, then the probability, sorry, let me write it a different way. If x is a random variable, then that is always greater than 0, then the probability that x is bigger than t is at most the expectation of x divided by t. Okay. So again, I'm assuming that most of you have seen this in your undergraduate probability classes. This is just a formalization of the rule from Perry Home Companion that not everybody can be above average. If there is a large probability that x is larger than t, well, all of that probability is going to contribute to the expectation of x and make it too big. Okay. So in particular, in our case, probability that the number of collisions is greater than 1, or let me say greater than or equal to, is less than or equal to the expectation, which is a half, divided by 1. So if we pick a random hash function into quadratic space, then there is at least a 50% chance that there will be no collisions. Everybody follow that? Any questions? All right, so this is the most common way to move from an expectation to a probability, is via Markov's inequality, okay? So now we have a probability of getting a perfect hash function, but we still don't have certainty. So what can we do to turn this probability into a certainty? Well, we can start by trying one, by trying to generate a hash function. So we'll try a random function. And if it's perfect, we can stop. We're done. Right? And notice that we have a 50-50 chance of success. But what should we do if we fail?
Try again.
Try again. Right? We just loop back to the beginning and try another random function. Okay. Now this algorithm, we can say, is guaranteed to succeed because it just keeps trying until it succeeds. Right? So this is guaranteed to eventually find a perfect hash function. How long is it going to take? Well, there's two things to ask about. One is how many iterations of the loop, and the other is how fast can we run each iteration of the loop. So how fast can we run an iteration of the loop? Well, generating a random function is very easy. And notice again, we're still going to work with pairwise independence here, because that's all that our analysis used. So we know that it's easy to generate a random pairwise independent function. How quickly can we check if the resulting function is a perfect hash function? What do we have to do? Have I lost everybody?
Hash all the keys.
Yeah, we just need to hash the keys, right? We just need to fill the hash table and see if there are any collisions. So that obviously takes us order n time. So one iteration of the loop takes order n time. What can we say about the number of iterations? Well, it's random. So it doesn't have a specific value. But what can we say about the expected number of iterations?
It's 2, I think.
2.
How come?
I mean, this is you have a set of, when you have a set of trials like this, I think the way the sum works out is it just equals 1 over the denominator. Sorry, so if you have probability 1 over k, and you're going to terminate once you, okay, so you roll a dice with k sides, and you stop rolling once you see 1. The expected number of time for that is, or the expected number of rolls for that is going to be k.
Exactly, and this is totally intuitive, right? Because in a uniform world, when you roll a die k times, you'll see each thing once. So that's kind of when you would expect to see the 1. So indeed, the expected number of iterations is equal to 1 over the success probability of an iteration, and is therefore at most 2 in our case, because we have a 50-50 chance of success. So overall, the expected runtime for generating this perfect hash function is order n. Just 2n. Yes? So now we have a mechanism for generating a perfect hash function. Actually, we have two mechanisms, and I'll just give you some vocabulary here. So this algorithm that we started with that had a 50-50 chance of success is what's known as a Monte Carlo algorithm. It's always fast, and it often works. And what we defined here by sort of doing this iteration is what's known as a Las Vegas algorithm, which means that it is always working. It always works. And it is often fast. And you can basically turn any Monte Carlo algorithm into a Las Vegas algorithm by just repeating it until you succeed. Going the other way, it's also possible to go the other way, but it's a little more complicated to describe. Okay, so now we have both Monte Carlo and Las Vegas algorithms for generating a perfect hash function. But it's still not really perfect in the Platonic sense because we are using n squared space for n items, which just doesn't seem efficient. So can we use less space? Maybe this bound that we had of n squared over s was not tight. Or let's say n squared, it was actually n squared over 2s, right? So might it be possible to prove a better bound and show that we can be perfect? We have a good chance of being perfect even with a smaller table? Well, let me give a concrete example of this. We've got some number of students in the class. Suppose that I asked all of you to state your birthdays. Okay, so I'm bucketing you, I'm hashing you according to your birthday. Okay, so 365 buckets. And we've got 37 participants. Is the chance of a collision small?
It's at least a half, right?
But if it were only a half, we'd be, I mean, that would be okay for our hash function, right? Because we were only arguing for a 50-50 chance of success. So I see in the chat, somebody has correctly asserted that it's much more than a half. Okay. This is an instance of what's known as the birthday paradox. Which says that once you have more than 23 people, the probability of a collision is greater than a half. And by the time you get to 37 people, it's very large. This n squared over 2s is pretty tight, actually. Okay. And the reason for that, let's think about putting you into your buckets one at a time. So the first person has no collision, right? But the probability that the next person doesn't collide with you is 1 minus 1 over s if there are s buckets, right? Because they have to avoid one bucket. Probability that the next person doesn't collide is 1 minus 2 over s because there are now going to be two occupied buckets, and so on and so forth, all the way out to 1 minus n over s as the, or n minus 1 over s, right, as the final person going in. And there's a well-known approximation. I can basically write this as e to the minus 1 over s minus 1 over, minus 2 over s minus 3 over s, all the way up to minus n minus 1 over s. This just uses the fact that 1 minus x is approximately e to the minus x when x is very small. And this denominator is actually the same thing as we just computed before. This is going to be e to the minus n squared over s or so. And so this is the probability of no collisions. And so once n squared is bigger than s, the probability of no collisions becomes very small. Okay, so if we don't make our hash table quadratic in size, we're almost certainly going to see collisions. Any questions about that? All right, I assume that all of you as MIT students know that this is a good way to, like, you know, win a bet at a bar. If you need money for drinks, you can just bet that there are two people who have the same birthday, and you'll almost always win. All right, so how can we get past this? We can use a very clever trick due to Fredman, Komlosh, and Zemretti. These are all very important people in complexity theory and data structures. Fredman was the Fibonacci heap guy with Tarjan. Komlosh gave some very interesting results on minimum spanning trees, and Zemretti is a combinatorialist. So they reckoned that you can address this, this limitation by introducing a second level of hashing. So what they said was, first, sorry, one sec. Yes, so what you'd first do is you hash your items to order n space. Okay. And this is going to give you some collisions, but not too many. And so that means that you need a lookup data structure in each bucket, right? And we were previously talking about a linked list, but why use a linked list? Let's build a hash table, a perfect hash table, on each bucket. Okay, so if we have B items in the bucket, then we will use B squared space in order to make it perfect. Okay, and so this gives us order one lookups, right? We, when we're given a key, we compute the top level hash function, and this gives us a bucket. And then inside of that bucket, we use the perfect hash function for that bucket, and we find the item in order one time. Yes? So the only question is, what is the total space? Well, it's n for the top level, right, where we store the information about the different buckets. Then we have to add up all of the buckets, which I'm going to note by k, of the square of that bucket size. Clear? Now, this quantity, this is where they do a very clever trick. What is bk squared? That's the square of the bucket size, but I can also just think of it as a sum of indicator variables, where I look at all of the items and have an indicator variable for which of them ended up in bucket K. Okay. And I'm overloading here. I'm using BK for the count and for the bucket. I'm sure you can disambiguate, right? So does everybody buy this step? So now I've got a sum squared. So I can expand that out as a sum of squares, right? Or a sum of products. Yes? Sorry, that's completely illegible. Somebody should yell at me when I'm not legible. All right. So I'm now taking sum of products of pairs of indicator variables, right? What does this mean? What is this product of indicators telling me?
Whether or not there's a collision.
Exactly. This is saying that I and J collide in bucket B, right? In bucket K. So if I sum over all of the events, all of the different buckets, these indicators for whether I and J collide in that bucket, what am I actually computing?
Just the total probability that they collide.
Well, there's no probabilities here,
Oh.
right? I'm working with indicator variables.
Yeah.
So what am I summing up?
Total number of collisions.
Exactly. This is just the sum of the CIJs, those collision indicator variables, right? Now, what do we know about this value? Well, now I can put an expectation around the whole analysis, right? And say the expected number of collisions is the expected value of the sum of the CIJs. What is that expected value? Well, we have to be a little bit careful because you notice that in this summation, somebody caught me before for doing a double sum. But here we really are doing a double sum, right? We are summing over I and J, and then we're later on summing over J and I. And we're also actually summing over all of the cases where I equals J. Right, so what we're actually looking at now is the expected value of the sum of all the CIJs, right? And so we actually have to separate out the sum of all the CIIs, plus now we can go back away from our double sum and sum over I less than J by symmetry of CIJ. Okay, so what is this value? We've seen this before, right? What's this quantity?
N squared over S.
Right, this is our N squared over 2S, right? What's this quantity?
Is it just N?
Yeah, every item collides with itself, right? So the quantity we wanted to compute, if we set S equal order N, then the expected sum of CIJs, or sum of BK squareds, is order N. In other words, if we use a size N top level table and then use quadratic second level tables, then the expected space usage is order N. Linear space and constant time lookups. Any questions? Well, I've got one. How do we get beyond an expected space usage to a guarantee?
Can we use Markov again?
Yeah, we use exactly the same approach. If the expected space is Kn, what we can do is generate one of these two-level tables. And then if the space used is less than 2Kn, we'll just stop. Otherwise, we'll repeat. Okay. Sorry, I shouldn't have used K. We already had that value. Let's call it, what's a letter I haven't used recently? A. So if the expected space is AN, no, that won't read very well. Sorry. If it's CN, then we stop when the generated, if we end up using space less than 2CN, otherwise we repeat. Why does this work well? Well, we're using the same paradigm as before, right? So Markov's inequality says that this is going to be, this is likely. The probability is greater than 1/2. So if our success probability is greater than 1/2, then the number of times we're going to need to try this is only 2 in expectation, and we get a Las Vegas algorithm for generating a perfect hash function with no collisions whatsoever. Any questions? All right. Just to wrap up, let me tell you about this quantity C, right? So if you just work through exactly what we did, you discover that C is about 13. That, you need to use about 13 N memory locations in order to get a perfect hash function, okay? With a little bit more work, just obvious things, you can get it down to 6 units, 6 memory words, or 6N memory words in order to build your perfect hash function. In this paper, the Fredman-Komlos-Zamoretti paper, they actually get it down to 1 plus little o of 1 memory locations, which is kind of incredible, right? So the amount of space that you need to use for order 1 lookups is the same as the amount of space that you need to look using just an array which you scan through every time in order to find the items. And they have to play some pretty clever tricks in order to do this. Basically, they store, what they recognize is that when you build your top level hash function, some of the buckets are going to end up with no items at all just because of randomness. In fact, a constant fraction of the buckets will be empty. And so they use those empty buckets to hold the extra information that's needed for the second level hash tables. It's very contorted, and that's never something you would do in practice, but it does show that from a theoretical perspective, this perfect hashing technique is perfect. All right, any questions? No? All right. There's one thing you can do to make it a little bit more perfect, which is to make it dynamic. So the method that I described for building this perfect hash table required checking whether it was perfect by hashing the items. So you can only do this if you've got the items in advance and are then building the lookup table. But what if you now want to support insertion and deletion? that's going to be, right, if you can support insertion and deletion, then somebody might insert items that destroy the perfection of your hash table. So figuring out how to extend perfect hashing to handle insertion and deletion took a couple more years. It's actually not that hard, and I'll probably put it on your problem set next week. Basically, the trick is that anytime your hash table becomes imperfect, you just build a new one. And all you have to do is prove that you don't have to do it too often. And you end up with an order 1 amortized data structure. Okay. So that's the end of our data structures unit. We're now going to switch to talking about combinatorial optimization for a couple of weeks. Now, before we, I'm just going to sort of outline our next problem today. But before I do, I just wanted to make one announcement in class. As I said at the beginning of the class in lecture 1, we are going to, we don't want people sticking with the same collaborators all semester. And so over the course of this week, we are going to arrange for a collaborator shuffle where you will seek out new collaborators for the problem set, which is going to be distributed next Wednesday. So by the time the next problem set comes out, you will have your new collaborator groups, so it will not be disruptive of your problem set work. We're pretty flexible about the shuffling. Our only firm requirement is that you not collaborate with the people you've already collaborated with. And the TAs will be following up with information about how we're performing that shuffle over the next few days. Okay, so combinatorial optimization. Until now, we've been doing data structures where you sort of store information and look things up. Now we're really going to be thinking about having an input and wanting to compute an optimal output for it. And so now we're not going to be talking anymore about runtime per operation. We're just going to be talking about the runtime of an algorithm. Okay. And the general notion is that any combinatorial optimization problem has a set of feasible solutions, those which are allowed, and each of those feasible solutions has a cost or a value, and you want to find the feasible solution of optimum cost or value, right? Sometimes you're trying to minimize the cost, sometimes you're trying to maximize the value. And for many of these problems, there's a pretty common paradigm for how you think about them. First, you understand feasibility. You ask, what defines a feasible solution? And you may actually talk about having an algorithm to determine feasibility. And sometimes even that is hard. Your next step might be an algorithm to find any feasible solution. Okay. After that, after you know how to find feasible solutions, you start thinking about solution value. And so then your first step might be to develop an algorithm to verify the optimality of a feasible solution. And only when you've gotten that far do you move on to figuring out how to compute an optimal solution. Okay, so often it's really daunting to get a brand new problem and jump right into thinking about how to compute an optimal solution. So instead, you work through it in these steps and you get there more easily. So we're going to do that with the first problem. which is the problem of maximum flow. So all I'm going to really do today is define it for you. You're given a graph G, and it's going to have m edges and n vertices. And in general, it's a directed graph. Undirected graphs are, of course, special cases of directed graphs, so we can talk about them too, but I'm going to talk about directed graphs for now. And you also have a specification of a source vertex, which is denoted by S, and a sink vertex, which is denoted by T. And a flow is an assignment of a number. Oh, sorry, not quite done yet. Along with the edges, you have a capacity, which is denoted by U sub E per edge E. Now, you may wonder why I'm using U for capacity. The reason is that we'll need C for something else in a couple of weeks. And so now a flow is a number per edge, which I will denote by F sub E. And we call it a feasible flow. So the definition of feasibility. If it obeys the capacity constraints, which says that the flow on each edge is positive, but at most the capacity of the edge. And it also has to satisfy what are known as the conservation constraints, which say that for any given vertex V, the sum over all of the other vertices W of the flow from vertex V to vertex W minus the flow from vertex W to vertex V is equal to 0, except when V is the source or the sink. So this is just saying that the total amount of flow entering a vertex has to equal the total amount of flow leaving the vertex, unless the vertex is the source of flow. And when you have a flow, we say that the value of that flow is just the sum over all of the neighbors of S of the flow leaving S minus the flow coming back to S. So again, this is the same form as the balance constraints, the conservation constraints, but it doesn't have to be 0. And in fact, the maximum flow problem is to compute a flow whose value is maximum, right? The amount of flow leaving S should be as large as possible. So this models many problems, right? But the intuitive one is that you just have a collection of pipes and you've got a source of water or oil or whatever other liquid you want to think about at one place in the pipes, and you want to know how much water you can push to some other place in this network of pipes. Okay, so you'll notice that for that sort of water example, the capacities and the flow values are probably going to be given in some rates, like gallons per second or something like that. But in the end, they're just numbers, and you can add them up and subtract them the way that I'm doing here. Okay, so are there any questions about this problem definition? All right, so the flow problem is the central problem in combinatorial optimization. It was first written about by Ford and Fulkerson in 1956. And there's two reasons that it is the central problem in combinatorial optimization. One is that there's all sorts of interesting theory that you can write about this problem. It's a complex problem, but you can really get a handle on it and prove all sorts of interesting facts. You can also develop all sorts of interesting algorithms. The other reason that it's central is that a tremendous number of real-world problems can be converted into flow problems. Sometimes the conversion is very direct, like when you want to move traffic through a city. And other times the conversion itself requires some creativity, but in the end you end up with a flow problem. And over the decades, we have developed incredibly fast maximum flow algorithms. The theory is running a little bit behind the practice, but even theoretically we can do quite well. And in practice, you can generally solve max flow in close to linear time. So it's incredibly powerful sledgehammer for a very large number of problems that show up in the real world. And we're going to be spending the next week sort of unpacking this problem, understanding how to develop algorithms for it, and just getting a more general sense of how one does combinatorial optimization. So that's it for today, and I will see you on Monday. Any final questions?